Hello, Honors Chemistry, and welcome to Chapter 7, Section 7.5, where we talk about aqueous solutions. So we discussed previously, right, that an aqueous solution had to be something dissolved in water, right? On the list of molecular compounds, again, molecular being the not ionic compounds, right, that you're supposed to know that are soluble in water, right? Sugar would be one that you're supposed to know is soluble in water, okay? Other than that, in the land of ionic compounds, and remember back to Chapter 5, you are able to name and discuss a whole boatload of ionic compounds, but that requires a little bit more thought, right? So first of all, ionic compounds are unique in that when they are dissolved, they dissociate into ions, yes? Right? So if we take NaCl and we dissolve it in water, right? What's going to happen is that it's going to dissociate into its respective ions, and that's true for any soluble ionic compound, right? Here we have AgNO3, which is a soluble ionic compound in water, and it's going to dissociate again into its respective ion. So here we need to be thoughtful, right, and make sure we're always layering in our Chapter 5 naming rules with stuff we know, right? We know that AgNO3 is composed of two ions, right? We have the nitrate polyatomic ion, and we have the silver ion. And that's what it's going to dissociate into, right? And we'll see that in these pictures here, right? There's water as the background, and then our dissociated ions, right? If we have an insoluble compound, right, like AgCl in water, AgCl is insoluble, right, meaning that it does not dissolve. And if it does not dissolve, it cannot subsequently dissociate, right, because it goes in that order. It dissolves and dissociates, okay? If it doesn't dissolve, it cannot dissociate. And what we would see at a macroscopic level is we would just see a bunch of solids sitting at the bottom of the beaker, right? In the case of AgCl, right? In the case of NaCl and AgNO3, we would see, right? For both of these, we would see a clear, colorless solution, right? In the case of, for example, CuCl2, right? That in water would be a clear blue solution, right? Because that's the color of copper chloride, right? But the point is they would all be clear because once it's dissolved, right, you can't visualize it anymore, right? Okay. In terms of what that means, a strong electrolyte, right, means that we have an ionic compound, right, that is soluble in water. And what happens is it dissociates into its respective ions, and those ions allow for conductivity throughout the solution, right? Pure water has no ions in it, right? And again, here we're talking about pure water, meaning water that does not have like dissolved ions like tap water would, for example, right? Or ocean water or pool water or any of those things, right? But pure water, no ions, little to no conductivity, right? And here, so this battery could well be like an outlet, right? It just has to be a source of electricity, right? And that source of electricity, and basically what we have here is an open circuit, right? And so if this liquid cannot conduct, right, we get no conductivity, right? And same thing here, right? But here we have ions, which allow for the conductivity, right? And then this light bulb lights up. And so a strong electrolyte solution is one that will conduct electricity very well. A non-electrolyte solution, right, so that's what this would be called. A non-electrolyte solution conducts little to none, okay? And then there's actually a place in between, right, which would be referred to as a weak electrolyte solution, which would fall somewhere in the middle, right? Where a non-electrolyte conducts little to none, a strong electrolyte solution conducts very well, and then we have weak electrolyte solutions where we dissolve something in water and it ionizes just a little bit, right? And that would mostly be, and we'll talk about it more later, right, our weak acids, right, which dissociate just a little bit, form a little bit of ions, and so we get a medium level of conductivity, right? So more than zero, but not a lot, okay? Which then this becomes conductivity becomes a way for us to check if something is a strong electrolyte, meaning does it dissolve in water and dissociate into ions. Okay. And then how will you know those things? Well, we have our table of solubility rules, right? So it's not like you can just know by reading the name of something if it's soluble, right? You have to memorize these rules, okay? And so we read them top down, okay? The top part are things that are mostly soluble, and here we have lithium, sodium, potassium, and we could just say all group 1 for that matter, okay? So we'll add in those other ones, right? All group 1s and ammonium are always soluble, right? So in the land of cations, all group 1s and ammonium are always soluble, right? So then, for example, if I had K Cr2O7, K2Cr2O7, and you'd be like, oh, I don't know if that's soluble. Well, you do, because potassium's in group 1. Group 1 compounds are always soluble. Yes, that's how that works. All right. And then we have for our anions, nitrates and acetates are always soluble, right? No exceptions, right? So if you had AgC2H3O2, silver acetate, you'd be like, oh, it's got acetate. It must be soluble, okay? Moving along, we have chloride, bromide, iodide. Note that fluoride is an exception here, right? So chloride, bromide, iodide compounds are soluble, right? Unless it's with one of these. These are exceptions, right? So what that means is PbCl2, insoluble, right? But, for example, NaCl, soluble, or FeCl3, soluble. Yes? Does that make sense? Right? Okay. And then sulfates are soluble with the exception of calcium, strontium, barium, or lead. Make sense? Okay. And then we go to the bottom part where these are insoluble except for the rules stated above, right? So hydroxides and sulfides are insoluble unless paired with one of those group 1 things, group 1 or ammonium, right? And sulfide has some rare exceptions there, okay? Carbonates and phosphates, insoluble, again, unless it's paired with a group 1 or ammonium, and then it would be soluble, right? So for example, sodium carbonate, soluble, right? If it were a group 2, like calcium carbonate, not soluble. Yes? All right. So then that brings us to that concept checked 7.4, which best depicts barium chloride in water. Well, we would go consult our solubility rules, which say that, oh, look, chloride is soluble, right? And our only exceptions are those. Barium is not one of those, which means this is soluble, right? And it's also ionic, which means it will dissolve and dissociate into its respective ions, right? Which makes this the proper one right here. This is showing you dissolved, right? But it's showing you that it's like weirdly dissolved into these like discrete molecules, which doesn't make sense because barium chloride is an ionic compound, not molecular, which is why this one's not true, right? This one is showing you that it is insoluble, right? So not dissolved. It's showing you that it's just a chunk sitting at the bottom of the beaker, which is also not accurate. Yes, does that make sense? How we rationalize which of these is correct? First, we'd apply our solubility rules and think about what it means to be ionic and soluble in water. All right. Thank you for listening. Be good and stay tuned where we take this and apply it to some reactions in the next one. All right. Have a good day. Be good. Bye.